While acid-catalyzed addition to alkenes typically gives the tertiary alcohol more than the secondary, more than the primary, we're also able to do this in the opposite sense by using a hydroboration-oxidation sequence. Here we'll see the addition of a borane in step 1, and then the oxidation of that borane in step 2 to give the less crowded, less substituted alcohol as the major product. The sequence begins with a concerted synaddition of the borane to the alkene through a transition state that avoids the clashing of large alkyl groups. Once the borane is formed, we then mix it with hydrogen peroxide and sodium hydroxide, and this produces the peroxide anion, which attacks the electron-deficient boron. The boron complex then undergoes a migration to lose the weak oxygen-oxygen bond, and that produces the borate as shown. This is then attacked by hydroxide, forms a 4-valent species which then collapses with loss of the alkoxide. This then deprotonates water from the solvent, and that gives us the alcohol product. Since boron is only 3-valent, it can accept a 4th pair of electrons, and when it comes close to the pi bond, it will coordinate with the pi bond and form a 4-membered ring transition state. In this transition state, the large alkyl groups, in this case a T-butyl group, and the parachute from the parachute borane will line up to avoid each other. And the outcome of this reaction is a synaddition as seen in the product, and this tells us that the mechanism must be concerted. The second reaction is to oxidize the boron and replace it with oxygen. So in this mixture, we see hydroxide reacting with hydrogen peroxide to give the peroxide anion. Since the peroxide anion is nucleophilic, it will attack the electron-deficient boron and produce a 4-valent boron complex. The borate complex features a weak OO bond, and so the molecule rearranges with migration of the carbon from boron to oxygen and loss of the OO bond in the form of hydroxide. And we know that this is a concerted process because the stereochemistry is retained. Since the boron is now 3-valent again, it can be attacked by the Lewis basic hydroxide to form a new 4-valent boron species. From here, the alkoxide breaks off and deprotonates the water solvent to give the alcohol product. The hydroboration-oxidation process with alkenes is therefore a method to undergo anti-Markovnikov addition of water. In the first step, we get a concerted synaddition to form the less hindered transition state, and therefore the secondary product in this case. And in the second step, the oxidation occurs with retention of stereochemistry in the migration step to give the alcohol as shown.